Hi there, I'm Riyos, and this is my presentation on functional programming. I will be discussing the primary objectives of the functional programming paradigm, reasons to use and not to use this paradigm, and a real-world example of how we use it in the industry level. So to start, what is functional programming? By its very definition, it's one of the main four programming paradigms, where it considers the logic and execution of our code to be pure, and that all variables are defined to be read-only, and every set of inputs to a particular function always return the exact output. So all operations are considered as mathematical functions. Let's take a look at how functional programming differs from a more imperative style. On the left, we see a familiar looking block of code written in Java which sums up all the values of an integer array. It defines a variable called sum, which is initialized to 0, and it uses a for each loop to visit each element in the array and add its value into the sum. When it finishes, it returns that sum value back to the client, the caller. On the right, we have a purely functional definition for this operation, written in a language called Haskell. First, we define the name of the function, SumList, and the nature of its input and output. You can see that we use numN to denote a variable called n, which is just of the numeric type. Over here, we define the input to be a list of n. Remember that n is a number. The square brace indicates that it's a list. Over here, the arrow points to the output, the return value of this function, which is just an n, a numeric. On the next line, we define the first action this function should take when it's given an empty list. In this case, we simply return 0 for all calls to an empty list. On the third line, we define the recursive step. We define two parts of this line with the notation x and xs. X is going to be the head, the first element of this list. Xs, which I'll just call xs, is going to be a list of every element after x. So it doesn't include x itself. It's only every single element following. In this step, we simply return x, the first element, added to SumList on the xs, every element that follows. So the function itself, as you can see, is pure. No values are mutated, only computations are performed. And when the computations are finished, so all these recursive calls are made, the value is finally added and returned to the user. Here's another example, one that's less trivial. In both examples, I'm using a syntax similar to JavaScript for your reference. On the left, we define a class representing a user for some social media app. It has many fields, but in particular, a field that represents the number of images the user has liked. Suppose we want to indicate that the user likes an image. In the imperative approach, we simply increment the user's num images liked field, among other business logic that's not relevant. In the more complicated functional approach, we have to do a little more. We first use this brace to indicate that we're copying a new value of the user. And I apologize, these should actually be curly braces to indicate an object, not an array. But anyways, we have the dot 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 user operation right over here to imply that we're making a hard copy of the existing user, which was passed as a parameter. However, with a caveat, the num images liked field is going to be different from the original user input. Instead, it's going to be assigned a value of whatever user.numImagesLiked is, the parameter value had, plus 1. And we're going to return that. So effectively, we're returning a brand new user that's the exact same, but only with one higher numeric value to its numImagesLiked field. Again, nothing is actually mutated, only new memory is allocated, copied over, and adjusted accordingly. You may be wondering why we would bother doing all that copying and allocating and writing over when it's just easier to access a single field and increment it. In fact, like for the computer, it's easier to do this because it's several less computations. You're only incrementing one field as opposed to allocating space and copying data over. This is why the purity of functional programming makes it fundamentally easier to debug. We can guarantee that the values and variables of the function as the function executes is predictable, so they aren't influenced by any outside sources or global variables or even signals. These functions are strictly defined by the parameters that are given to them and the actual core logic of the that defines this function. Because these functional programs are so predictable, they're inherently more easier to debug because we can make certain guarantees and assumptions about the state of the code as it executes throughout the program lifetime. If there are any assertions we need to make about our algorithm regarding the correctness, we can make a formal, rigorous proof that the function behaves as expected. And this idempotent property is highly desirable when we're developing code that resembles mathematical functions, just like we do in cryptography. I also mentioned that it's more efficient for the computer to simply increment the single field of the user data structure. Although functional programming requires several extra computations to allocate and copy over the memory, most compilers nowadays can actually simplify the task. Most compilers would see what we're trying to do, copying a new data structure and creating a new data structure and copying the memory over, and they could just simplify that down for us into a simple increment operation as needed. Of course, I'll tell you that there are some cases where you don't want to do that. Anyways, I've given you some reasons why we use functional programming. I want to pause and give you some food for thought. Why wouldn't we use functional programming? Are there any specific examples where functional programming isn't useful?
Well, one reason is that functional programming has a learning curve. I'm going to show a more complicated example of functional programming later in the presentation, but just from this example where we mutate user data, I'm sure you can tell yourself which example is easier to understand and even teach to a novice programmer. Functional programming isn't very intuitive, and most people begin their programming careers within more of an imperative mindset. So the effort to migrate code between one code base that's imperative and a new one that's functional is incredibly difficult and honestly more costly than the like output you would gain from doing that. In addition, there are some tasks in software development that are inherently impure, like file operations or database updates. Just the simple task of writing to a file, a memory buffer, or even the console requires data to be mutated. On the operating system, where the hardware is constantly communicating with each other via signals, those signals need to mutate some form of in-memory data to indicate that they happened so that other events and software processes can respond accordingly. Low-level mutations like these could never truly be expressed in a functional language or a truly functional style. So, I've given a lot of discussion about the pros and cons of functional programming and how it works. I'm going to end the presentation with a real-world use case of functional programming. I'm sure we've all heard of the React library, a very common JavaScript library for developing front-end applications. Right here, I have a very common example of the reducer pattern, which we use in React. It takes a variable called state, as you can see right over here. In this case, for me, state is just an array of items, and it takes an action, which can be anything, really. It can contain any data, which indicates what we need to do to the state. In my example, action has an item, which is something that we might want to add or remove to the state array, and it can have an ID, which is probably just going to be the ID number of the item. Um, so um, for some background, the React documentation requires that reducer patterns have to be pure so that we don't change any of the values in either of these parameters. Most specifically, the state variable. We cannot change that value. This is to ensure that the state variable is updated properly by React under the hood, and also it's to ensure proper coding standards. It's way easier to debug this function when you know exactly what the input is and and you know what the output is, and state variables in between are not modified. This function doesn't perform any kind of impure operations, and for those reasons, it's a lot easier to track what's going on in the program and what got updated when. But looking at this function in particular, you can see that first I check to see if the state, in the add case, when we see that the action is an add, we check to see if the item is already in the state. And if it's not, we're going to duplicate the state array and add a new item, which is just the item in question that we're trying to add. But if we see that the state array does contain this item we're trying to insert, what we do is we simply just create a mapping on the current state array. A mapping in functional programming or functional style programs will take the contents of the array and perform an operation on each element within the array. So in this case, for me, it's this function right over here. I'm not going to get into detail. I challenge you to scrutinize this function and tell me whether it's correct or not. But this function will be executed on every item in the array, and then the return value of this function is added to a new array, and then once this function is called on every element in the original array, the new array will be the exact same length as the original array, and that is what the map function finally returns. Or in this case, it's what I return. And then in the clear case, we simply return an empty array. Again, in no place is the state array ever mutated. It's only scrutinized, read, and computations are performed with its values in consideration. And also here is the remove case. Just like with the code over here in the add case, I challenge you to scrutinize this code yourself and conclude whether it's correct or not. But to conclude my presentation, functional programming isn't simple. I've been working with functional programming for quite a while, and I do see the appeal of simply using imperative code, where we mutate data as we need to. But I will admit that functional programming, the very paradigm, makes code that's predictable, easy to prove, and easy to debug, because we don't have to go through multiple different places and modular components of the code, multiple different areas to look at every single variable that our function depends on and figure out why it's being mutated when it shouldn't be. We know that the code execution is predictable and behaves as we expect it to. So for that reason, I do agree that debugging is simpler when we are using a functional programming style. And I suppose this is the reason why it's so popular in industry level development nowadays. These are my works cited. They were very helpful in putting this presentation together, especially when I was considering a real world example of functional programming and when I wanted to compare it with object-oriented languages like Java.